We're on to Unit 10 now. This is vectors. So the two things that I want to do today with you are to discuss what a vector is. That's basically section 10.1. And then I want to talk about how you do math with vectors. And for that, I'm going to talk about section 10.2, which is the part where you start to take vectors and do stuff with them. Um, Afterward, when we finish that, I might spend some time intermittently in this lesson talking about what how you actually geometrically deal with vectors, how you draw them and what they mean. So the first thing I want to ask you is, or what I want to define for you is what a vector is. So I've made a table here on the first page of the lesson, and this is available on Blackboard right now. So let me just zoom in a lot here. So a vector, and let's just do that here. I'm going to highlight a little bit of coloring. It's coloring with John. Ready? So what is a vector? A vector is any quantity that has a magnitude and a direction. So when I say magnitude, I mean anything you can think of that's quantifiable, like a number. So for example, if I say to you, how old are you? Then you could say, oh, I'm 22 years old. Okay, that's not a vector though, because 22 years old is just a magnitude. Whereas if I said to you, where is the store? You could say, oh, it's 300 meters east of where you are. That's different. See how you put east on that? So a direction and a magnitude both together make up a vector. If you cannot apply a direction to a quantity and it's just a magnitude, we call that a scalar. So in this table below, I've kind of alternatingly put different quantities for which there are scalar or vector quantities associated. For example, distance. Distance is a scalar, 20 meters. Now you might say, wait a second, John, can't you put like east on that? You can, but distance is something that you measure with a ruler or with a tape measure. Like if I say to you, how tall are you? If I say to you, how tall are you? You could turn around, let's use centimeters, and you could say, oh, I'm 180 centimeters tall. You would never say, I'm 180 centimeters tall up. Why would you say up at all? Or how long is the couch? I have to fit it through the doorway, or whatever it is, like if you're moving, or any quantity that you can have doesn't necessarily, in the correct context, need to have a direction associated. And sometimes you just can't have a direction. Like volume. Look at volume, right? Okay, what's the volume of that really big fish tank at Ripley's? Oh, it's 100 cubic feet. You would never say 100 cubic feet north. Doesn't that just sound ridiculous? In the chat, let me know. 100 cubic feet north. Doesn't that in your head just sound really, really weird? Like it does not make sense to say? It just kind of bugs me, doesn't it? I totally, James, it just bugs me. Or here's another one. Would you ever say this to somebody? Hey, John, what's the temperature outside? Oh, okay, it's minus 10 degrees Celsius. See, that's a temperature, you know that. And then someone says north. Would you ever say north beside a temperature? Doesn't that sound ridiculous? You would never put a north after a temperature. So some quantities inherently, without even being a physicist or a physics student or whatever, you just would never drop a direction on that quantity. Here's one that's often screwed up by people, and pardon for the lack of formal language there, definitely screwed up, is when people say speed. See, here's a speed, 40 miles per hour, and then they'll drop a direction on that. They'll say, and I see this on the news. I see this on the Weather Channel. Or maybe not the Weather Channel, but just like the regular news. And they'll say like, oh yeah, the winds have a speed of 40 kilometers an hour west. Why are you dropping a west on that thing? It's speed. Speed does not have a direction to it. If you want to put a direction on something, where it involves motion, for example, linear motion, you would put velocity. See, there's velocity. And you see how now it has a direction. It says S 20 degrees east. So that's saying that it's somewhere in between south and east. By the way, we'll discuss this notation of south 20 degrees east soon. It's going to play a significant role in today's lesson. So be prepared. We'll discuss it soon enough. But for now, just think about it that it's somewhere between south and east if you're looking on a grid. There's another one that's often a little bit more subtle, and it's the thing here, position and displacement. So at this point, I just want to say that whether or not you've taken physics before in your life, it's not going to be dangerous for you because I'm going to teach this from scratch. All of these quantities that you see here that are vectors, like position, displacement, and velocity, and force, I will discuss these quantities in a very meticulous and patient way in Unit 11. So all of that stuff, all these things here, are really associated with more of the application side of vectors, where you're taking the idea of a vector, the construct, and you're putting it in a practical situation, and you're doing stuff with it, calculations and application. So all that stuff is next booklet. For the next 2 weeks, we're just talking about what a vector is and how you do some basic math without any words like apply or solve or anything like that. And in terms of position and displacement, I will take significant time in the third lecture, so not this lecture, but 2 lectures from now. I'll take significant time discussing the difference between position and displacement, because even if you've studied physics, I don't necessarily think that if I asked you it right now, you could give me a very clean application / definition. So anyway, so I'm having a tough time highlighting there, but you can see that displacement and position, the difference really is that position has a reference point. So position is more about where you are relative to somewhere else, like a reference. And then displacement is about, it describes how you moved yourself from one point to another. I think that even without having a background in physics at all, you still have an idea of the word displacement in some way being to move or to go from A to B. Displacement, you can think of it as going from A to B. Finally, we have another quantity that's a vector here, which is force. Now, you all are familiar with the word force, but definitely, may not most likely have seen force in the context of a math or a physics class. So I'll just let me know in the chat. I just want to see, because I got about 23 people here. Let me see who's taken physics and or calculus before. So let me know in the chat if you don't mind. Okay. Okay. So it's kind of a split down the middle. Now, I'm going to be honest with you. There's two things that are going to happen here. Not bad. 11 physics, I'd say that's cool. That's good enough to be with the grade 12s as well. So there's 2 audiences here that I'm dealing with. People that have seen this stuff before and people that haven't. Now, I'm going to teach it at a level where it's, if you haven't seen it before, you'll understand and you'll be good. But the good thing is if you've seen it before, just because you've seen it before doesn't mean that you've seen it with me, obviously. And I do have some very slick ways of doing things, and I'll share those things with you, those techniques. And hopefully, by the time you do finish with me this vectors and applications, you might take away something different or new, or even improvement on how you were problem solving in the past. I want to talk about this east and north business, and that's what we're going to spend some time doing right now. So take a look at this grid here. As you can see on the axis here, we have north up here, east, west, and south. And we're going to take a lot of time today doing something that is very mundane, very boring, but boring means that it's easy, hopefully. And what I want to do is talk further about this. How do you interpret this on a grid? So that's what I'm going to do with you right now. But to do this, I'm going to have some, I'm going to use some notation that you might have seen back in grade 11, or you should have seen in grade 11. So I'm going to draw an axis here, and I want you to think about angles in standard position. So this is something that you did a while ago, probably in grade 11, angles in standard position. So can someone tell me what that means, angle in standard position? Who remembers that from grade 11 math? Who remembers anything about that in grade 11 math? The silence is deafening. Okay, let me remind you. Let me remind you a little bit. Here's an angle. If you measure it counterclockwise from the x-axis, there's the x-axis. Let's write that down. This angle, as long as the two arms of the angle have an origin at the origin of the grid, then this angle is said to be in standard position. And what that means is that you can assign a number to it between 0 and 360 degrees. So for example, this is 0 degrees, and as you go round and round, counterclockwise, this is 90, this is 180, this is 270, and then you go back home again, and this would be 360, etc. Okay, who remembers this vaguely? Who remembers seeing this in high school somewhere? Okay, anybody else? I'm mostly interested in the ones that haven't taken any physics before. I only see 2 people. Nobody else remembers doing this in high school? Another trigger word might be this. Who remembers this? Cast. Who remembers cast? Anybody remember cast? Cast rule, or whatever you call it? Yeah, the quadrant stuff, Jai. That's right. Quadrants, all that stuff. Okay, that's fantastic, everybody. Because if you don't remember it, well, now you have it here, okay? So what I want to do now is spend a large portion of today's time talking about how you take a direction like south 20 east and turn it into a number from 0 to 360. So the exercise today for the first hour, a lot of it is going to be this. Turning a direction like south into an angle in degrees. And that angle there is going to be between 0 and 360. So that's our exercise today. And then after we've done that enough times, and you've gotten sick and tired of me showing you the same thing over and over again, then we'll do actually a foundation, a building block for next time's class. So here's the first question. 16, Nikita, you're a champ. Stick around at the end of class, okay? And if you have a way of sharing your screen with me or something, I'd love to see your solution, because I have not gone through it fully, as you can see, and it would be very interesting to see how you did it. Okay, express the following direction as an angle in standard position. North. So, you did it with AutoCAD. Okay, now you definitely got to share your screen after. Now you got me intrigued. As you know, everybody, there's no assignment today, so I don't think we're gonna go straight to 11. We're probably gonna finish earlier. Anyway, can someone give me the angle for north? So here's north, right? What angle is north from 0 to 360? Yeah, that's right. It's 90 degrees. 90 degrees. Okay. What about east? Yeah, it's 0 or 360 or any multiple of 360, including negatives. Sorry, this thing is a little glitchy. Yeah, it's 0 degrees. I'm gonna put square brackets on this because it does represent a direction of some sort. Okay, so I'm gonna go a little quicker on the first four because I do think that these are the easier ones. Okay, someone else in the chat. What's west? What would west be? Thank you. So west is 180. And finally, south. So what's south? What is south? How many degrees? Okay, I want to see at least 10 people in the chat let me know that what they think of this. Hopefully they think this is easy. Let me know in the chat. Do you think what these 4 examples are easy? I'm seeing some new names. Thank you, everybody. I know that it's early. Oh, there we go. Got some new names here. Thank you, Christopher. I'm not going to say them name by name, but thank you, everybody. That's awesome. So, for those that are not sure what's going on here, remember, this is 0 here, and as you go round and round and round, that's what I'm saying, okay? So in this case, you're just going this much, which is a right angle. This one's just 0 because it literally is on the x-axis, pointing east. And I'll just keep on putting 0 here to remind you, you're going all the way here. And then this one here, you're doing a reflex angle of 270 like that. So anyway, hopefully that wasn't too dangerous for you. But now, these things here represent really the annoying things that come up later. 22 degrees north, what the heck is going on over here? Okay, let's draw a picture. These come down to drawing a picture. I don't care if you draw the picture on paper, but at least either you understand it in your head, you can visualize it, or you just draw it on paper. So 22 degrees north of east. So I'm going to draw an angle. Okay. It's not 45 degrees, but I'm being a little bit lazy there with my I'm not drawing at the scale. So what I want to ask you is, where do I put the 22? Do I put the 22 up high, or do I put it down low? Does the 22 go high or low? What do you think? So we got a split between Jai and Sean here. So who's on the Jai camp? Who's on the Sean camp? High or low? Anybody? We need a tiebreaker. Okay, well the answer is low. The answer is low. You guys are too dangerous for me. Let me explain why though. Let me explain why, okay? The wording's a little bit different here, but I know I will definitely I'll definitely explain it both ways. So you see how it says of east? See the words of east? So what that means is that east is your reference, and you're gonna go relative to east. Okay? So it's relative to east. Sorry, I'm having trouble with this drawing here on relative to east. So if you had switched it the other way, here's the other way. You see how it says east of north? Now it's the way that you were saying on the high camp. It's this way. So that angle's 27. But what's the answer? If I go back to the previous question, I failed to write down the answer here. The answer to this question is 22 degrees because it literally is measured from east. My apologies for that. I didn't clarify that. Okay, now let's take it slow here. Thank you, Jai, and thank you, Sean. So does everybody see that in the chat there? This angle up here is 27, but we don't want that angle. We don't want that angle. We need the angle relative to the x-axis and counterclockwise. So if you do 90 minus 27, you get 63, which is exactly what I was. I'm just copying exactly what your friends have in the chat. So the way that it works, everybody, is you look at the word of, and the direction that follows. This is not the only way to write these directions, so I'll just do this one here, and then I'll backtrack and talk about the previous ones again, writing them a different way. West of north. So it's of north, so that means you're going to go from the north axis and rotate west. So this is 13 here. That little arrow there is 13. Sorry, that little angle there is 13. So here's 0. What would be the final answer here? 103. Okay, how did you get that number? I know that's a really easy calculate. Thank you, Anthony. So you did 90 plus 13. I realize that there's people in this audience that are getting a little bit scared about with the angle and do you add or subtract and whatever, and it's weird. I got good news for you, and I'll share the good news with you right now, okay? If you go to page 1 of the notes, thank you, Anthony. If you go to the front page, this happened about 2 years ago or 3 years ago in class, and I just said, you know what, let me just make a diagram. So the diagram's right here, everybody. If any of this stuff is bugging you, just print page 1 or just screenshot this little thing here and have it on a sheet of paper beside you as you're doing any of the calculations for Unit 10. That's the next thing I want to talk about, Jai. Thank you, Jai. The next thing I want to talk to you. No, there's no quiz today. No quiz, Aaron. No, it's in the course. No problem. You're welcome. In the course outline, it clearly says there's no quiz. So I'm not saying that to you specifically, but some people emailed me saying if there's a quiz, and I'm just like, look at the course outline. It's right there. Okay, so I want to go back and just address another thing, and Jai brought it up, and I was about to bring it up too, is that this thing over here, this direction, you can write it a different way as well, which is east 22 degrees north. So that's the alternative to writing it. In the booklets that I've made, in this booklet specifically, I have done everything in terms of using the word of. All the work that I'm doing in this booklet, I use the word of. So the way that it is in red, I don't do it this way in this booklet, but you are responsible to know both ways. So I didn't want to confuse people by bouncing back and forth between the two notations. So that's why I just did it the of way. So this way you have it always one way. It's a little bit more inflexible, but it is consistent. So that's so if you like this way and you have training doing it this way, just do it this way. If you like what I'm showing you here and you want to adapt to that, do it this way, the way I'm showing you. The reason I'm showing you this way is because the book does it this way as well. Actually, the book does mostly this and a little bit of that. But anyway, I'm going to take this direction here, and I'm going to copy it to the next two questions, just to have it on as a comparison. But I'm not gonna do it for every question because it's honestly just changing 2 letters. So this one here, just trying to get it up here. There we go. So this would be north 27 east. And just the next one as well, just so that you have a few of them to just solidify that pattern. So that would be north 13 west. I think that, like you might argue which way is the easier way. It really depends on the audience too. I think that because for me, like someone has a background in math or computer science or something like that, I like this way in red here, like saying north 13 west, because it's very like, I don't know, it just looks like I'm writing a coordinate or something, even though these are not coordinates. This one here is more like, if for someone who's like a visual reader that likes to see the grammar of it as well, so west of north, the word of there gives you the flavor that it is of relative to the north axis. So that's something that's personal to you, and I respect that. But in the meantime, let's just go through. I got another what? 8, 9, 10, 13, 36, 6 more of these. So what I like to do is let's do all 6 of these questions, and then we'll take a short break, and then we'll continue with the material. And hopefully that's a rewarding experience, and we can move forward. So you can use the template on the first page if you like. I'm just going to draw them myself, and it is what it is. So if you want, just do the next 3, and I'll catch up to you. So I'm just setting up all the answers. 74 south of west. So it's of west. So here's the west, and you're going to go to the south, like that. So that's 74 degrees. So what is the angle that goes in this box here? What angle goes here? What is the standard angle? Yeah, you're going to take 180 plus. Thank you. So 180 plus 74. So that's 254, 254 degrees. For those that are like, why is it 180? Because this is 0 here. Remember, 0 is over here. And you're going round and around to that point. That's 180. But you want to go further by the extra 74. Okay, who has the final answer to question number 9? What's the final answer to 9? Thank you. Okay, Gianluca, tell me in the chat. Thank you, Jai, as well. Gianluca, tell me in the chat how you got that. Tell me what calculation you did. Let the class know what your calculation was. Thank you very much. So you did 360 minus 38. So what I'm going to do right now is just show that diagram for everybody. So you see how it says of east? So here's east, and you're going to go to the south. So the angle is this angle, but we have to go counterclockwise. So this angle here, sorry, this angle in the gap here is 38, but we don't describe the angle like that. We have to go counterclockwise from the x-axis, just like when you learned the CAST rule in grade 11. So it looks like Pac-Man, sort of. Okay. A lot of these questions, for me, it was like you just close your eyes and you can just kind of visualize it, or you just draw the thing. What's the final answer, number 10? Someone new? Anthony. Oh, you're a champ. You're a champ. Look at that. Okay, I gotta catch up. This is like A plus, A plus. Okay, so we have so it's of south. So here's south, and you're going toward the west. So this little angle in the gap here is 29. So, but if I go this way, I gotta go all the way this here. That's the angle that I want in standard position. So I gotta take 270. Thank you, Anthony. I gotta take 270. We don't quite get to 270. 270 is right there. We're just shy of it. We have to deduct 29. And that's how you get 241. Okay, here's a few more. These ones I'm not going to accompany with a diagram. I'm just going to do the math. Okay, thank you, Anthony. So this next one here, the calculation is going to be 180 minus 81, which is 99 degrees. This one here. Anybody have a value there? 298. Can someone confirm? Thank you, Anthony. How did you get that, Anthony? Well, thank you. I didn't mean to confirm the answer, sorry. I just wanted to know the calculation for the class. All right, one more to go. Oh, it's the same answer. Yeah, that was deliberate on my part. Yep, Dante, I'll do this last one here. I'll do these two with a chart, 100%. So let's do this one here. So we have of east, and it's to the south. So this is 62 degrees because it's relative to east. But then you have to go all the way around this way. So if you were to go all the way around, it'd be 360, but you don't get there. You fall 62 degrees short of that angle of 360. So that's why. I'll draw the last one fully. So this one is east of south. So here's south, and you're going a little bit toward the east. You're going 28 degrees toward the east. So that angle measured from the x-axis, if you go all the way to here, it's 270. But you got to go the extra 28 as well. Whoops. I guess I can't draw that arrow again, so I'll just redraw it. You got to go the extra 28. No, AO, it's always counterclockwise because that's the convention for the angles in trigonometry for the cast rule. Standard angles, I should say. When you have standard angles, you always go counterclockwise. And there's different conventions for angles. There's ones that involve bearings and other things like in the military, but we're not doing bearing notation here. I forgot my plus sign. So in this course, I'm not using any bearings. If bearings do appear anywhere, I promise you I'll give you like a heads up on that, whether it's a hint or some type of coaching there. So we're going to take a break shortly, but I do want to talk to you a little bit. I'm just not going to record that part for the final presentation. So we're going to do calculations now involving components of vectors. And it comes down to taking a vector here, which does not necessarily align to a specific axis, in this case, the x and y axis. And we're going to just find out how much of this vector here is going with the x-axis and how much of the vector is going with the y-axis, or in that direction. You can actually do the calculations really easy because we know angles in standard position. So we're going to take fx here and fy, which are the components of the vector f, and we might use other letters depending on what the context is, but the key thing you need to remember is that it's f cos theta and f sine theta. For those that have studied physics already, you might say, hey buddy, wait a second, the x component is not always cos and the y component is not always sine, like they flip-flop sometimes. But if you use an angle in standard position, it will always work this way. So let me just type that here. So just emphasize that to you, okay? If you're going to use the angle in standard position, the way that I've been showing you for the past half an hour of real instruction, it will always be the same thing. I think someone's mic's on. Yeah, Jai, that comes up later. That's next week, actually. That's next week. So today we're just taking a vector and breaking it into pieces, and then next week we're going to reconstruct the vector. So that, and also do some other stuff with it. Sorry, I'm just opening up a different file here. So just bear with me for a second. When I make the video for this later, I'll edit out this stuff, me talking. Okay, so we're going to find out the x and y components of this vector v here. In this case, it's a velocity vector. So let's talk about how you do that. Notice how the velocity vector has a magnitude, which is 513 meters per second. Those are units of speed. But then there is a direction applied, which is 32 degrees north of east. So you see in combination, the magnitude and the direction give us a vector quantity. And on that vector quantity, you can see that there's an arrow on top of the symbol for v. So when you communicate a vector to somebody on paper, you should always write a vector with an arrow on top, and then make sure that you have a direction, usually and in my class, preferably with square brackets around them. So let's talk about how you would do the answer to this question. The first thing you need to do is find the angle in standard position. So can someone tell me what the angle is between 0 and 360? Yeah, it's 32 degrees. So the first step is to get that angle. Now, if anybody's wondering why is it 32? Is it always the same number? No, you have to do the picture. So what I did with you in the first hour, or first half hour, I should say, is I did this diagram. So there's the angle, and this is 32, which conveniently is the easiest case outside of the axes. So I'm just going to put a happy face there because that one is super easy. I promise you the future ones, you're going to have to like sweat it out a little bit. So now that we have that angle, then we can say that the velocity vector in the x direction, like that, is equal to 513 meters per second. Well, it's not letting me do it the other way, so that's fine. All good. Cos 32 degrees east. And then the y component is going to be the same thing with sine and north. Let me know in the chat, please be honest. Let me know in the chat if you have any questions about what I just wrote on the screen. I want to be careful and clear about everything. Let me know in that chat. Do you have any questions about the three things that I wrote here? Okay, can someone do the calculation then and provide us with the numerical values? Thank you, Jai. So the x component for the velocity is going to be 435 meters per second east. And the y component is going to be 272 meters per second north. So those are the answers for the components. I want to support this diagram with the diagram. So I'm going to take this diagram here and I'm going to just erase the 32. Let's get rid of that. And I'm going to draw a better diagram with the vector itself. So here is the original vector. Here's the original vector. It's not to scale. That's v. And you can think of this vector as having two components. One component acts in the horizontal direction, which is the east direction. There's Vx. And the other component acts in the y direction, which is up here, which represents in this context north. X and y could also mean different things if you're looking at it from the side, like up, and to the right or something. But anyway, this is the diagram that describes the following scenario. Are there any questions before I proceed to the next example? Okay, well, you have everything you need in your pocket now. Once you get that angle, you're good to go. And I'll show you how valuable it is to have the standard angle. So some of you might be like, this whole angle here that I'm doing, like this 298. Why is 298 better than 28? I will talk to you, I will convince you, sorry, in the future examples on its purpose and its value. So let's do the next question. Here we go. So we have 38 degrees west of north. I'm going to draw my axis over here. Now 38 degrees west of north is somewhere here. So what's this angle here? Can someone give me that angle? What is that angle there? That's right, Gianluca. 128 degrees. And just for emphasis here, that is because it's 90 plus 38. And this little thing in here is 38. That little angle there is 38. In terms of the components of the vector, I'll draw them in purple. There's a vector going up, which represents this position in the y direction. And there's a vector going to the left, which is the position in the x direction. So my question to you is, how do we do, like what I'm showing you, will it help us? Because this thing here is west. I wonder what's going to happen when I just use 128 degrees. So let's take a look what happens when you use 128 degrees. I want you to see that something very magical happens. So what is 372 cos 128 on your calculator? It's negative. Whoa, wait a second. Negative. Okay, I'm going to put east here, right? That's east. But you said it's negative. That's so weird. Let's take a look and see why that is the case. Negative 229 meters east. What's negative 229 meters east? What is the opposite of east? What is the negative of east? Thank you, it's west. Let me know in the chat. Did that make sense? So if all of this is a little bit scary for you, let me show you how I do it a little bit more safe. Because these arrows here might be scaring the crap out of people. So this is what you can do. Just write dx without an arrow on it. And don't worry about this east anymore. Just ignore it for a second. This is how I would write it if I was a student. On the safe side, I would do those calculations first. And then, once I have this answer, then I can interpret that in the context of a vector as being this. So the step, everything in black is supporting calculations, and the final answer is the red answer. You got that? The black stuff is there to support you, but the final answer is the red. And what I'm doing here is, yeah, it's negative, all good. That negative means west. So positive is east and negative is west. You can do the same thing in the y direction. Bear with me as I copy and paste here. So the y component would be sine. And someone have an answer there? What will be the y component? Is it positive or negative? And what's the number? Thank you, Sean. It's 293. And is that north or south? Do you get a north or south answer? Thank you, Ravindra. Yeah, you get a north. Look at the picture over here. The x component was pointing this way to the left. Now, it's not left in this case, it's west. See how we got west here? And you see how the y component was pointing up, or in this case, north. And you got a positive number over here. Because this is always the case, when you use the angle in standard position, you don't have to worry about drawing a picture, because it will always work out correctly. If you use the angle in standard position, you do not have to draw this picture at all. And that's very powerful, because then you don't, without drawing a picture, that means it's a lot easier to do the work. For those that have studied physics, they might remember that doing components of a vector, or breaking a vector up into x and y components, it was annoying because you had to draw a picture and take a look at what it was. Who remembers having to draw a picture and it was annoying all the time drawing the picture? Maybe not annoying, but it wasted a lot of time. Who remembers drawing the pictures and wasting time getting those components? Anybody remember doing that in the chat? Anybody found that annoying? Nobody remembers doing that? Oh, Abdullah, my friend, stick around at the end of class. I want to see your explanation. I'm very Very enthusiastic about this. Can someone give me the angle between 0 and 360, please, for 56 south of east? Does anybody have the angle for question 16 in standard position? 304. Very good, Sean. Notice that I'm not going to draw a picture for this question until I finish the question, because you don't actually need to have the picture. That's what's amazing about this method. So Fx is going to equal 842 newtons. In this case, it's a force. It's newtons. Cos 304. And Fy component is 842 newtons sine 304. Can someone calculate those quantities? Anybody have those answers? What's 842 cos 304? So that's 471 newtons. This n here does not mean north. And what is the sine? What do you get for that? Okay, what I want you to do now is interpret that by writing down the actual component now. So what is the x component going to be? 471 newtons. What goes in here? East or west? East or west? Yep. Okay. Can someone else in the chat let me know? I want to see some other people here. I want to see other people as well. 698 newtons. Is that north or south? Someone else, north or south? Thank you, Brian. Did I draw a picture for this question? Absolutely not. I was able to figure out the answer with east and south without drawing a single picture. But now I can draw the picture and confirm that the numbers in the calculations were consistent. So if I draw my vector is 56 south of east, so this is 56 degrees here. If you go around this way, that's going to be 304. And this is 56 over here. But when I look at the components, let me draw an arrow on that vector. When I look at the components, there's a component facing south and there's a component facing east. And that's exactly what you have here. You have an east and a south component. So everything aligns with the diagram. This component is 471 newtons east, and this component is 698 newtons south. And everything was automatically found once you had the standard angle. You see how everything worked out, the plus and the minuses, everything dealt with? A negative sign appeared here when you did sine. Like, it all worked out beautifully. Some of you are probably wondering, why does it just work out? Like, how did it just work out miraculously that you get east and south without having to draw a picture? And the reason that it works is because of the cast rule. Because when you use an angle in standard position, all of the signs follow the cast rule. So I'll just say that here. That's why it is the case. The cast rule, it aligns perfectly with what we need. Sine is positive, cos is positive, sine is negative, cos is negative. Or sine is positive, cos is positive, and cos is negative. I said that totally wrong. Anyway, let me write down the cast rule here and clarify that. Cast, okay? Here's cast. Can someone tell me where is sine positive? Where is sine positive? Which of the quadrants? Yeah, these two, right? Sine is positive here. So take a look here. The y component is sine. And notice that the answer is positive. In other words, whenever sine is positive, it's on the top, so that's north. And whenever sine is negative, you get south. You can apply the same logic to cosine. So sine is negative at the bottom here. And you can see that the cast rule fits perfectly with up and down for sine, and it also fits perfectly for left and right with cosine. So that's why it is so nice. That's why it's so nice. Let's keep on going here and try some more examples, and maybe take away a little bit less of the drawing and focus more on just the computation. In this case, what is the angle in standard position? I'll draw the picture for that, but then proceed with the calculations independent of the diagram. So 26 degrees west of south, that's 26 right there. So what's the angle then? Instead of 26, what angle do you get here? So how do you get the angle, theta? Yeah, west of, oh shoot. That's my apologies. 26 degrees west of south. So what is the angle that you get? Or how do you calculate it? Anybody? What's the angle in standard position? Thank you. So let's get those components of the acceleration vector. So first we're just going to find out the calculation, and then we'll present it nicely after. Can someone do those calculations? So what's the first one? What's 2.14 meters per second squared cos? Yep. Yeah, I got the same. I'm going to put an extra decimal there. And for the y direction, there's no significant, or there's no precision or accuracy asked for in the question. So I just went to 3 decimal places in my solutions. But Jai's answer is just as correct as mine, because I didn't specify. But let's communicate though the correct answer in terms of a vector. Maybe I can squeeze it in over here. Probably can squeeze it in right here. What direction goes in this bracket? What goes in this bracket here? Is it going to be north, south, east, or west? Anybody? So it's going to be west. It's going to be west because it's in the x direction, and in the context of this question, x is either east or west. So that's this one right here. Now the last one is going to be north or south, and that's going to be 1.923. Is that north or south? South. So I have a typo here. There should be a minus sign. That's my apology. My apologies there. I thought I put a negative sign when I typed it. Let's draw the vector here. I'll draw it in this yellow color. So that's this one here. And then the original vector here is the diagonal. Okay. Let's do one more. And then what I'll do is we'll take a second break. And then during that last break, there's like 7 questions. And I'd like you to try a couple more. And then the rest you can do for homework eventually. Very straightforward lesson. And yeah, that's about it for today's class. So let's keep on going here with one more. So we have a velocity vector that is east of south. So I'll just draw the directions up here. East of south, so here's south and you're going to go east. So this angle here is 81 degrees. Maybe I'll do a better scale there. That's 81 degrees. So then the The standard angle is all the way around like that. Can someone confirm? They agree with that? Any people confirm that? So that's 270 plus 81 degrees, or 351 degrees. So then you have Vx. So Vx is going to be 28.4 meters per second. Post 351. And Vy. I hope that you're getting the feel for that. It's a very routine thing to do now. It's not like every question is a new adventure. It comes down to getting the angle, a skill that we focused on in the first part of today's class. And now this is always going to be cos and always going to be sine for x and y respectively. So it becomes a very nice procedure. The first answer is 28.05. That's what I got. And for the second one, I got negative 4.44. Okay, what goes in those brackets? What direction goes in this one up here? East. Thank you. And what goes in this one over here? All right. Who has never taken physics before, but has the hang of this or gets it? Who's feeling good about this, but never took physics before? Who's feeling good about this, but never took calculus or physics before? Who didn't? Okay, beautiful. That's my target audience. I mean, everybody's my target audience, but when I see people that have not taken calculus or physics, that's beautiful. That's my target right there. If you understood this, then I know that I'm doing a good pace. So everybody, it's almost 10 o'clock. There's no assignment today, but we can definitely spend some time in the third hour for those that want to stick around. I'll do a couple more after the break. What I'd like you to do now is just take 10 minutes on your own and do 19 and 20. So I will scroll out. Hopefully your screen size is good enough to read that. Is that good? I think that should be good enough. If you don't have the thing in front of you. I'm going to take up 19 and 20 in 10 minutes. Okay, so I'll be back at 10:05, 10:07. Okay? Take 10 minutes and do these two questions. And do 19 and 20. We'll be back at 10:07, okay? So yeah, see you in 10 minutes. Question 19, the standard angle is going to be, let's take a look here. The standard angle is going to be north of west. So what would that angle be? Between 0 and 360, what would the angle be? That's correct, Jai. Now, I am going to refer to the answer key because you did have a 10-minute head start against me, so there you go. That's straight from my answer key. And these answers will be available on Blackboard at the end of class. So hopefully you got these numbers. The main thing here is getting that 161 degrees. For those that weren't sure about where that is, 161, it's north of west. So this little angle in here is 19 degrees. But the angle measured from the x-axis for the purposes of standard position is that angle, which is 180 minus 19, or 161. Once you have that angle, you apply the two component formulas right here. These are always the same. It's always cosine. That's a typo there. Sorry, I'll fix that typo. So you get that component, and then after that, you're good to go. So you see here that we have a negative in the x direction, which makes it west, and a positive in the y direction, which makes it north. So question 20, I'm just going to type out the answers for this one because I think it's better if I go a little slower. The angle in standard position for 20 is west of north, so that's 90 plus 25. If anybody here is like, you know, maybe you missed the beginning of class, I have a shortcut on the first page here that can give you the answers to those angle permutations. So they're right there if you need to use that. That's on page 1. I'm just going to get back to example 20 now. So that's 90 plus 25 degrees. So this is a momentum vector. So in px, we'll have 47.5 cos. In this case, that's 115 degrees. Notice that I'm not trying to be sloppy here, but now I'm not putting the angle, sorry, I'm not putting the units here. I'm just doing the calculation kind of quickly on the side. And then in my final answer, I tend to be obviously very picky with the units. So if I forget to put the units on the intermediate calculation, it's not really being a good role model for you, but it's not the end of the world here if you do that, because this is all just supplementary calculations anyway. These are here to support the final answer. So the y component of momentum would involve the sine, not cosine. And then if you evaluate that, I got negative 20.1 kilograms meters per second. And for the sine, I got 43.0. Can someone confirm those in the chat? Can someone confirm that in the chat, please? Thank you. Thank you, James. Then we have 20.1 kilogram meters per second. And what direction goes for the x component? Is it east, west, south, north? What is it? That's right, it's west. Thank you, Jai. And let's do the y component. Don't mind me copying and pasting. Just trying to be efficient with you. So that's 43.0. Is that north or south? Thank you, James. And there you go, my friends. So we went through many of these questions, and you'll see that I've left you with 4 of them. So just take your time. You can think of them as homework if you like, and definitely go back and try those questions. I encourage you, though, greatly to make sure that you visit the textbook and to do the recommended questions in the textbook. So in terms of this material, you're going to be going to chapter 9 in the textbook. See, it says section 9.1. And then for the second part of today's lesson, you're going to go to section 9.2. There are many examples there, and you have a list of recommended questions available on Blackboard. So please, please, please make sure you do many recommended questions, because when I give you your assignment next week, your assignment is based off of the textbook's database. So what that means is that the questions will look like your textbook. Yes, I'll go back to 20. Sorry. Sorry about that. There you go. Make sure you go to the textbook and do questions, because your assignment next week is based off of the textbook questions. Okay? Very important. It's not a catastrophe. If you understood what I showed you here, you're fine. But in any case, your textbook will have questions in there as well. I'll try to keep the assignment as close aligned as to what we did today. So anyway, what I'd like to do before we end is talk a little bit more about the geometry of vectors and how you add them together. So these last 4 questions, you can do those. but I want to just talk about very briefly when you add two vectors together, how you actually do it on paper with geometrical insight. So this is a preview of what we're going to do next week, but I thought I might just bring it in here as extra knowledge. So if you want to add two vectors together, let's say you want to take this vector A, I'll call it A like that, and then you have vector B. Let's say B goes this way. There's many ways of adding vectors together, but in terms of like what I'm going to show you here, I'll show you two constructions. The first way is what's called the tip-to-tail method. So the first method is called the tip-to-tail method. So the tip-to-tail method literally means you take the two vectors. Here's the first vector. It doesn't matter which one you use first. So I'll just use this one first because I feel like it. It doesn't matter which one comes first. And you just kind of put them together tip to tail. You see that? You connect them tip to tail. So if these were like describing, for example, you going on a journey, it makes natural sense that you go here and then you go here. And if there's a third vector or whatever, you just keep on going like a journey. Think of it like you're going on a trip. Anyway, when it comes to adding vectors together, the ultimate answer here, or the addition or the sum of the two vectors, depends on where you start and where you finish. I start here and I finish there. So the resultant, or in other words, the sum of the two vectors is right there. That's A plus B. So A plus B is the sum of the two vectors. And that's called the resultant. So that's one method, which is called the tip-to-tail method. There's a second method, which is called the parallelogram method. The parallelogram method, as you might understand, would involve a parallelogram. So I'm going to draw a parallelogram using the two vectors. So what you do is you take the two vectors. So there's your first vector. And you would do this to scale if possible. But you draw them like that, tail to tail. And then what you do is you construct a parallelogram. So these two vectors form the edges. Now I got to do it as best as I can here. You see how I'm drawing a parallelogram using the two vectors? They form part of that perimeter. And then what you do is you draw a diagonal across the middle, and that represents the resultant. See, like that. So that's the second method, where you draw a parallelogram. These two approaches for adding vectors together are very nice when you only have two vectors. But when you have more than two vectors, as you can imagine, with more than two vectors, it gets a little bit out of control. So that's where the components, which is what I'm showing you today, becomes very valuable as a method. So what I'm going to focus with you on next week is how you take more than two vectors and add them together using a method of components. So what we did today was the foundation of that method. I will introduce a lot more geometric insight at the beginning of next class to explain the method of components and to motivate you for why it's useful. And from that point, we'll recycle many of the examples we did today will be recycled in terms of their style in the upcoming class. So that's it for today's class.